Welcome, curious minds, to the deep dive. You really think of digital security as these, impenetrable fortresses of code, complex mathematical equations, and layers of encryption, right?
Yeah, it all sounds very abstract, very digital.
Exactly. But what if the very physical way those algorithms run on a tiny computer chip could leak your most sensitive data?
Mm.
Imagine a master key to your digital locks, not stolen through sophisticated hacking, but simply observed as the lock turns.
It's a compelling thought, isn't it? We often focus on the digital, the abstract vulnerabilities.
Right.
But hardware itself, the physical substrate where all that code lives, it has its own unique set of whispers. These aren't digital footprints. They're more like subtle physical cues given off as the chip performs its operations.
And here's where it gets really interesting.
Huh.
Our mission today is to unpack precisely this hidden world of side-channel attacks on cryptographic devices, specifically zeroing in on power consumption. And the good news is, we're not just highlighting a threat, we're diving into a fascinating new countermeasure designed to fight back, something called a physical time-varying transfer function, or TVTF.
And what's truly compelling about TVTF, I think, is that it offers a generic, low overhead, and digital-friendly solution. This isn't just theory. It has the potential to dramatically enhance the security of the countless embedded devices that are all around us.
Devices we often don't even notice.
Exactly. Unnoticed, yet profoundly important to our daily lives.
We're drawing our insights today from some cutting-edge research. The paper's called Physical Time-Varying Transfer Function as Generic Low-Overhead Power SEA Countermeasure.
That's the one, by Arkisman Ghosh, Debayan Das, and Shreyas Sen from Purdue University and the Indian Institute of Science.
These are really the folks pushing the boundaries of what's possible in hardware security.
Absolutely. And why should you care about this deep dive? Well, in our increasingly data-driven, internet-connected world, IoT world, the security and confidentiality of communication, of computing, it's absolutely paramount. It really is. Think about everything from your smart home devices, lights, thermostat, to the microcontrollers managing critical functions in your car, or even the small chips in your wearable tech.
Right.
Protecting these embedded systems from subtle physical vulnerabilities isn't just a technical challenge. It's crucial for your privacy, your safety, and the integrity of the data you generate every single day.
So this deep dive, it's going to offer you a shortcut to understanding a complex, vital area of modern cybersecurity that's often overlooked. So let's unpack this and start with the invisible threat itself. Power side-channel attacks.
Okay.
So we're talking about side-channel attacks, SCA. What exactly are they? Is this like a classic hack where someone exploits a flaw in the software or, breaks an encryption algorithm?
That's a great place to start because it's fundamentally different from traditional hacking. A side-channel attack isn't about breaking the mathematical integrity of a cryptographic algorithm itself. The algorithms, like, say, AES 256, they're still mathematically sound. Instead, it's about observing side-channel information that inadvertently leaks out when that algorithm is actually implemented and running on a physical platform, like a microchip.
Ah.
It's kind of like listening to the faint sounds a safe makes as someone tries to open it, rather than trying to guess the combination itself.
So the math of the safe is perfect, but the physical turning of the dial, or in this case the chip's operation, reveals a secret. What kind of information are we talking about here? How does a chip leak?
Precisely. The chip might leak information through various physical phenomena. The most common examples include minute variations in power consumption, electromagnetic or EM emanation, the precise timing of operation.
That thing too.
Oh yeah, or even things like cache hits and misses on a processor. For this deep dive, our primary focus is on Power SCA because it's proven to be one of the most common and potent attacks on embedded systems today.
Okay, that makes it sound quite serious. But just how dangerous can observing power consumption really be? I mean, we're talking about powerful encryption like AES 256, which I understand is incredibly robust.
It is incredibly robust, mathematically speaking. For instance, breaking an AES 256 engine using a brute force attack, meaning just trying every possible key combination.
Guessing, basically.
Right, guessing. It would require 2 to the power of 256 attempts. That's an astronomically impossible number.
Like more than atoms in the universe kind of number.
Far more, yeah. Effectively making it unbreakable through pure computational guessing.
Okay. So mathematically impossible.
But a power SCA attack can dramatically reduce this complexity. Instead of 2,256 attempts, a successful power SCA might reduce the effort to something like 2 to the power of 13.
2 to the 13, that's tiny in comparison.
Exactly. To put that in perspective, it effectively breaks the encryption by reducing the key search space to just 256 possibilities for each of the 16 key bytes.
Wow.
That's a staggering reduction in complexity, turning an impossible task into a very real and achievable threat within a, reasonable time frame.
Wow, that's a huge difference from literally impossible to something that's suddenly within reach. So how does an attacker actually do this? What are the mechanics of a power SCA?
The process typically involves several sophisticated steps. First, an attacker needs to precisely measure the instantaneous power consumption of a target device, like an AES encryption engine, specifically during its encryption phase.
Right.
They use specialized, high-resolution equipment to capture these tiny fluctuations in power over time.
So they're essentially listening to the chip's heartbeat as
Yeah.
it performs its cryptographic work.
That's a very apt analogy.
Yeah.
Next, they synchronize each captured trace, which is the waveform of power consumption over time, with either a chosen plain text,
Data they feed in.
right, data they feed into the device for encryption, or a known ciphertext, which is the encrypted output they observe. This synchronization is absolutely crucial because it aligns the power signature with specific operations being performed on known or guessed data.
And then, once they have enough of these synchronized power traces, that's when the analysis part comes in. How do they actually extract the key from what might seem like a lot of noisy data?
Precisely. With sufficient traces collected, they perform what's called a differential power analysis, or DPA, or a correlational power analysis, CPA attack.
DPA or CPA?
These are powerful statistical techniques. The attacker will have a model, basically a hypothesis, of how the power consumption should behave for different possible key values based on the data being processed. Then, they take their measured power traces and try to correlate them with these hypothetical models. The key byte hypothesis that shows the highest statistical correlation with the actual measured traces is likely the correct one.
And are there different models for this power behavior? Like, does it matter if it's software encryption versus hardware encryption? Do they consume power differently?
Yes, the specific power model is critical and depends on the implementation. For software cryptographic implementations where data moves in and out of registers sequentially, the Hamming weight HW model is often employed.
Hamming weight.
Yeah.
Number of ones.
Exactly. This model predicts power consumption based on the number of ones present on the data bus or within a register during a switching activity, as more ones generally correlate with higher power.
Okay.
For hardware cryptographic implementations, where operations are often highly parallelized and the same register might be updated repeatedly, the Hamming distance HD model is typically used.
Hamming distance.
Bit flips. Right. This model focuses on the number of bits that switch from one state to another, say from a 0 to a 1 or vice versa, because these actual transitions consume the most power.
So they pick the model that best fits the target's architecture, essentially understanding the chip's language of power. Can you give us a real-world example of this kind of setup, perhaps like the researchers used?
Certainly. The paper describes a very common setup in hardware security labs. They used a chip whisperer platform.
Chip Whisperer. Cool name.
Isn't it? It's an open-source tool specifically designed for side-channel attack research. This platform allowed them to precisely measure the power consumption of an 8-bit Atmega microcontroller running an AES 128 encryption algorithm.
Okay, so a standard microcontroller.
Yeah, this kind of setup allows researchers to simulate a realistic attack scenario and rigorously test the effectiveness of any countermeasures they develop.
That sounds like a sophisticated lab setup for a very specific type of eavesdropping. What's the main metric we use to quantify how effectively a device resists these power attacks?
The key security metric here is the minimum traces to disclosure, MTD.
MTD. Okay.
MTD represents the minimum number of encryptions an attacker needs to observe and analyze to reliably reveal the correct secret key byte.
So fewer traces needed is bad news.
Very bad news. Naturally, a higher MTD means the device is more secure against power SCA. For an unprotected software AES 128 implementation, the MTD can be frighteningly low, sometimes as few as 20 to 200 traces.
20. That's almost instantaneous for an attacker with the right equipment.
It really is.
So if it only takes 20 to 200 attempts to crack a key, that's incredibly quick. This brings us to the urgent motivation for a new solution. Why is this threat growing now, especially with the explosion of IoT devices?
Well, Power SCA has been a known threat for over 2 decades, but its urgency is escalating dramatically. And it's largely due to the proliferation of miniaturized, resource-constrained Internet of Things, IoT devices.
Right, they're everywhere now.
Exactly. These small, often inexpensive devices are everywhere, from smart sensors to connected home appliances, and their inherent characteristics can make them particularly vulnerable.
I would have thought smaller devices, which are typically low power, would mean less leakage and therefore be less vulnerable. Is that not the case?
It's a common and counterintuitive misconception. While 8-bit or 16-bit microcontrollers do consume very low power overall, they frequently exhibit a high signal-to-noise ratio, SNR, in their power traces.
High SNR. So the signal is clear relative to the noise.
Precisely. This means the specific data-dependent power leakage, the bits that actually reveal secrets, is clearer and less obscured by other electrical activity compared to, say, a much more complex 64-bit processor.
Oh, okay.
Those larger processors, with their multiple cores and complex operations, they generate a lot more algorithmic noise that can inadvertently mask the sensitive signal. Because side-channel attack models often target individual bytes or nibbles of data, these simpler high SNR architectures are actually more prone to successful correlation attacks.
So the very simplicity of these widespread IoT chips, the thing that makes them cheap and efficient, ironically makes them more exposed.
Yeah.
That's quite a twist.
It really is.
Given this widespread vulnerability in devices we all use, what's urgently needed then? What are we looking for in a good countermeasure?
We urgently need countermeasures that meet 3 critical criteria for real-world adoption. First, they must be low overhead.
Meaning chief in terms of power, area, performance?
Exactly. They shouldn't add significant cost in terms of power consumption, chip area, or performance degradation. Second, they need to be generic.
Like a wrapper?
Yes, meaning they can be used as a wrapper or add-on without requiring modifications to existing cryptographic algorithms. This preserves legacy code and simplifies integration. And third, they must be synthesizable.
Synthesizable means easy to manufacture.
Yeah, basically. It means they can be easily scaled across different technology nodes in manufacturing without manual, time-consuming effort, thus reducing non-recurring engineering costs.
That makes perfect sense. Low overhead, generic, and synthesizable. Those are the critical factors for widespread industry adoption. Now, let's explore what's already out there and why it hasn't quite solved the problem. What does the landscape of existing countermeasures look like?
Okay, so the state-of-the-art hardware countermeasures against Power SCA generally fall into 3 broad categories: logical, architectural, and physical.
Logical, architectural, physical. Okay.
Each category has its distinct approach, but also, crucially, its significant hurdles.
Let's start with the logical countermeasures. What are they trying to do, and where do they typically fall short?
Logical countermeasures focus on designing SCA-resistant logic styles right at the very gate level of the chip. The goal is to sort of equalize power consumption in each clock cycle, trying to make it harder to extract data-dependent leakage.
Trying to make every operation look the same, power-wise.
That's the idea. Examples include techniques like dual-rail precharge logic, or DRP, and other logic-level hiding schemes such as sense amplifier-based logic, SABL, wave dynamic differential logic, WDDL, and bridge boost logic, BBL.
These sound like very fundamental changes to the chip's design. Are there downsides to such a deep-level approach?
Absolutely. The main limitations are quite significant. These techniques often require custom library cell design, which is both expensive and time-consuming for manufacturers. More importantly, they tend to incur large area and power overheads or lead to substantial performance degradation. For example, WDDL, while showing an improvement in MTD, did so with a staggering 3x increase in chip area, 4x higher power consumption, and a 4x reduction in performance.
Yikes. 3x area, 4x power, 4x slower. That's huge.
It is. So essentially, you're often trading off a massive chunk of performance and chip real estate just to get some protection. That's a non-starter for most resource-constrained devices, especially in IoT.
Yeah, absolutely. It sounds like rebuilding the engine every time just to make it a little more fuel efficient.
Yeah.
So what about the architectural countermeasures? Do they tackle the problem at a different level?
Yes, architectural countermeasures operate at a higher level of abstraction. They utilize things like time or amplitude distortions to hide leakage. This category includes techniques like the random insertion of dummy operations.
Sake calculations.
Kind of, yeah. Or shuffling the order of cryptographic operations, clock randomization, and random order execution.
Randomizing the order of operations sounds intuitively like it should work. Why isn't that a complete solution?
Well, while intuitive, these shuffling techniques are typically limited by the specific cryptographic algorithm and architecture. They're not generic.
Oh, no wrapper.
Right. And they usually involve modifying the algorithm itself, which makes them less flexible as a universal wrapper solution and often provides only limited protection. Moreover, clock randomization, like dynamic voltage and frequency scaling, DVFS.
Changing the clock speed randomly.
Yeah, that's been shown to be defeated. An attacker can simply observe the shifted clock edges at the power supply and compensate.
So they can undo the randomization.
Pretty much. The leakage still happens, it's just shifted in time, and that shift can often be accounted for.
That makes sense. If the pattern is still there, just moved, an attacker can learn to find it. Yeah. So what's the third category? Physical countermeasures.
Physical countermeasures involve direct physical interference with the leakage itself. One well-known scheme is noise injection.
Just add noise.
Basically, yeah. Attempting to overwhelm the data-dependent signal with random electrical noise. However, this often suffers from extremely high area and power overheads, making it impractical for many devices. It's like trying to yell over the whispers, but you end up needing a massive megaphone that consumes too much energy.
Right. Are there other physical approaches beyond just brute force noise?
Yes, other techniques focus on supply isolation, trying to isolate the crypto core from the main power supply. Things like low dropout or LDO, regulators, and buck converter integrated voltage regulators, IVRs, have been explored.
Do those work?
Well, LDOs have been shown to be inherently insecure in ideal implementations, and buck converter IVRs suffer from significant area overhead due to needing embedded passive components like inductors.
Okay, so still hurdles. Anything else?
There's also signature attenuation, which aims to reduce the signal-to-noise ratio. It can be efficient, but it often uses mixed signal circuits.
Analog and digital together.
Right. And those are notoriously difficult to scale consistently across different manufacturing technology nodes.
It sounds like everything has its own set of significant problems or unworkable trade-offs. This brings us to a specific predecessor that the paper discusses, the switched capacitor approach. This seemed promising, but had its own fatal flaws, right?
Exactly. One notable precursor was the switched capacitor current equalizer proposed by Tokunaga and his colleagues. The core idea behind this was quite clever: to isolate the AES engine from the main power supply using a charging capacitor.
Okay, so use a capacitor as a buffer.
Sort of, yeah. Preventing direct observation of its power fluctuations. It operated in 3 distinct phases. First phase, a load capacitor would be charged from the main power supply.
Charge up the buffer.
Then second phase, this now charged capacitor would completely isolate and drive the cryptographic core, like the AES engine. So it was entirely disconnected from the main supply during its sensitive operations.
Total isolation.
And finally, in the crucial third phase, the capacitor would be actively reset, discharged to a fixed voltage. This last step was designed to prevent any residual charge or data-dependent leakage from being passed back to the supply in the next cycle, sort of wiping its memory.
That sounds like it provided very good isolation and control. What kind of protection did it offer?
This countermeasure actually provided very high protection, achieving over a 2500x improvement in MTD. It was quite effective in principle.
There's always a but.
There's always a but. It came with major practical limitations. It suffered from a 2x throughput degradation, essentially halving the performance of the crypto engine. And to achieve similar performance, it required using very large capacitances, which led to more than a 2x area penalty on the chip.
Ouch. Half the speed, twice the size.
Yeah, and the reset phase you mentioned was crucial. What was the problem there, beyond the power overhead?
Right, what was the real killer?
The reset phase, while vital for security, required an analog bias voltage. This made the entire solution fundamentally non-synthesizable.
Ah, back to synthesizability.
Exactly. It couldn't be easily designed and scaled using standard automated digital fabrication tools across different technology nodes. This significantly increased its cost and complexity for mass production, making it impractical for widespread adoption in commodity hardware. Plus, actively resetting capacitors like that inherently increases power overheads, too.
So it worked well, but it wasn't practical for wide-scale adoption because of those analog components and the design challenges. What happened when researchers tried to make it synthesizable by removing that problematic analog reset phase?
That was the next logical step. Researchers then attempted a 2-phase switch capacitor without reset. The idea was to remove the complex analog reset phase, making the design more digital-friendly. In this simplified setup, 2 capacitors would alternate. While one capacitor drove the AES core, the other would charge from the main supply.
Did that solve the synthesizability issue?
It did, but it introduced a fatal security flaw.
Yeah.
The residual voltage on the capacitor after it had driven the AES engine, which contains that data-dependent leakage information, would then directly connect back to the supply when it was charging.
It leaked the secret back out.
Exactly. This direct connection effectively leaked the very information they were trying to hide. This approach only provided a very small MTD improvement, less than 10x. It just lacked true supply isolation and thus effective protection.
So getting rid of the analog component made it practical to build, but completely undermined its security. A classic fix one problem, create another scenario.
Pretty much.
What about simply using a multi-phase switched capacitor in a deterministic way? Did just adding more capacitors or more predictable phases help?
That was indeed the next avenue explored. Researchers investigated the effect of charging multiple capacitors together or using more phases in a deterministic, predictable way. They studied whether introducing nonlinearity or a kind of memory effect by partially charging capacitors could enhance security.
And what did they find? Did more phases help?
Their findings were quite revealing. Deterministically introducing nonlinearity or a memory effect by charging multiple capacitors did not significantly enhance MTD.
Really?
Yeah. In fact, in some cases, adding more phases in a deterministic way even showed lower MTD. This was partly due to how the fixed total capacitance was distributed among more units, which could sometimes reduce the overall isolation effectiveness.
Huh.
This crucial insight revealed that a simple multi-phase setup without a clever twist isn't enough to provide robust side channel protection. The key was not just more phases, but how those phases were managed.
That leads us perfectly into the TVTF breakthrough. If deterministic multi-phase capacitors aren't enough, what is the clever twist the researchers discovered?
The crucial insight from this research is the introduction of controlled randomness.
Randomness, okay.
If simply using multiple deterministic capacitors isn't enough, what if we randomize how they connect to the power supply? The core innovation of the physical time-varying transfer function, or TVTF, is to achieve significant time domain obfuscation by randomly shuffling distributed switched capacitors.
So instead of a predictable pattern, it's like scrambling the pieces of the puzzle just as an attacker tries to look at them.
Precisely. By randomly changing which capacitor is active at any given moment, the information content in the power traces can be dramatically reduced. The attacker sees a chaotic, obfuscated signal rather than a clear, repeatable pattern linked to the secret key.
Like adding static to the signal.
Kind of, yeah. If you could see the power traces side by side, an unprotected AES trace might show clear, rhythmic pulses corresponding to operations. But a TVTF-protected trace for the same operation looks like a dramatically obscured, noisy mess. An attacker would find it nearly impossible to decipher.
That makes intuitive sense. Now, you mentioned this is physical shuffling as opposed to algorithmic shuffling. What's the distinction? Why is that important?
That's a critical distinction, and it speaks to the genericity we discussed earlier. Many existing architectural countermeasures try to randomize instructions at an algorithmic level, literally shuffling the order of operations in the code.
Changing the software.
Right. But those approaches are often limited in scope and tend to be specific to particular algorithms. TVTF, however, operates at the very VDD or power supply level with switched capacitors. This makes it a physical obfuscation technique.
Affecting the power delivery itself.
Exactly. It's a fundamental change in how the power is delivered and consumed, independent of the algorithm's internal steps.
So it's not changing what the chip does, but how it gets its power to do it. And how does it compare to clock randomization, like DVFS, which we discussed earlier as being potentially vulnerable?
It's superior to clock randomization because DVFS merely shifts clock edges. An attacker can often defeat that by simply observing those shifted edges and adjusting their timing analysis.
So just readjust their stopwatch.
Kind of. TVTF, on the other hand, fundamentally alters the signal itself by randomizing when specific leakage events occur, effectively scattering the information across time and different physical paths. This makes it far more difficult for an attacker to synchronize and correlate traces as the underlying signal itself is being distorted in the time domain.
So it's not just moving the chair, it's physically scrambling the entire room, making it hard to find anything. And the ultimate benefit here is genericity, meaning it can be used widely.
Yes, its genericity is a huge advantage. This technique is truly generic and easily applicable as a wrapper to any cryptographic algorithm or processor core without requiring modifications to the core's internal logic.
That's powerful.
It makes it highly adaptable and valuable for a wide range of embedded systems, offering a universal layer of protection.
Okay, I'm intrigued. How does this TVTF algorithm actually work? Give us the step-by-step of this random shuffling.
Okay, the core mechanism is quite clever. It involves a total of n capacitors, which are dynamically divided into two distinct arrays. Let's just call them the Toby charged pool and the tow supply AES pool.
So one group is waiting to get power, the other group is waiting to give power. Makes sense.
Exactly. Now, in each clock cycle, the algorithm performs two critical simultaneous random selections. First, it randomly picks one capacitor from the tow supply AES array to drive the AES engine.
One powers the AES.
Right. This ensures the AES core is always isolated from the main supply by a capacitor, never directly connected. Second, it simultaneously and randomly picks one capacitor from the to-be-charged array to connect to the main power supply for charging.
One gets charged up.
That's right. So at any given moment, the AES is driven by one randomly chosen charged capacitor, and another randomly chosen capacitor is being replenished from the supply.
Okay, and then...
And here's the clever part. After a very short predetermined time, these two capacitors, the one that just drove AES and the one that just charged swap arrays,
they switch pools.
Yep. They are then ready for the next random selection in the following clock cycle. This dynamic random shuffling ensures that the capacitor driving AES is always isolated from the main supply, and its leakage components are constantly being mixed and redistributed in time, making them incredibly difficult to track.
How is this randomness actually achieved on a chip? We're not talking about dice rolls, I presume.
No, not dice rolls. The randomization is achieved using linear feedback shift registers, LFSRs.
LFSRs. Okay.
These are sophisticated digital circuits, you can imagine them as very complex digital dice, that generate high-quality pseudo-random numbers. For their implementation of a 10-phase TVTF, the researchers utilized a specific design of LFSRs capable of producing a unique sequence of patterns for a very long time, specifically 255 different combinations before repeating.
255 states. That's a decent amount of randomness.
It is. This long, unpredictable cycle is absolutely vital to keeping attackers guessing and ensuring the shuffling patterns are sufficiently varied.
And what about safety? Does the random selection ever accidentally connect the AES directly to the supply or try to charge a capacitor that's also driving the AES? That sounds like a potential short circuit or security vulnerability.
That's a crucial point, and the digital logic implementing this algorithm is designed with safety as a top priority. It explicitly ensures that the same capacitor is never connected to both the main supply and the AES at the same time.
Okay, good.
This critical safety mechanism prevents any direct leakage path from the AES to the main supply and also prevents any dangerous electrical configurations.
So the randomization itself has low overhead, but can an attacker figure out the random sequence from the power traces? If they can predict the shuffle, the protection is gone. Right.
That's a valid concern for any randomized countermeasure. However, the power consumption of the LFSRs themselves is significantly lower, like orders of magnitude lower than the AES engine's power consumption. Much quieter. This makes their contribution to the overall power trace minimal and often buried in noise. Therefore, it's extremely difficult for an attacker to extract the LFSR's initial seed from the overall power traces or to reverse engineer its sequence.
That's a huge advantage, effectively hiding the very mechanism of the defense.
Yeah.
And in real-world scenarios, can this randomness be made even stronger?
Absolutely. Modern microcontrollers often come with built-in true random number generators, or TRNGs.
TRNGs, right? Hardware randomness.
Exactly. These TRNGs produce genuinely random numbers, and they can be used to provide even stronger, truly random seeds for the LFSRs used in TVTF. This would further enhance the security of the TVTF without adding significant additional area overhead to the chip.
Making it even more practical.
Yeah.
Okay, so the random shuffling of capacitors is key. Now, there's a fascinating, almost counterintuitive truth the paper uncovers about the TVTF design. It's about why sometimes less can be more. Can you explain that?
This is indeed one of the most interesting and non-obvious findings of the research. Let's first consider the probability of leakage when we select just a single capacitor to drive the AES, which we denote as M1.
Okay, M1. one capacitor selected.
Right. So if a specific capacitor, let's call it clique, has just driven the AES at a moment in time, it now contains some residual voltage carrying sensitive information. This clique then gets moved into the to-be-charged pool.
So it's holding some leakage memory, like a secret message that's been partially erased.
Exactly, a good way to put it. Now, according to the algorithm, in the very next time step, the algorithm will randomly pick one capacitor from that to-be-charged pool to connect to the supply. If n is the total number of capacitors, the probability that that specific clique capacitor will be chosen to connect to the supply at that next step is 2n.
Okay, 2 divided by the total number.
Right, and this probability further reduces over subsequent time steps, meaning the leakage information is effectively diluted across time and different capacitors.
So if you have 10 capacitors, the chance of that specific one leaking its information to the supply at the next immediate step is 2 out of 10, or 0.2. It's a low chance, meaning the information gets spread out and hard to pin down.
That's correct. This dilution is key to the obfuscation. But here's where the counterintuitive part comes in. The critical question then becomes, what if we choose multiple capacitors simultaneously, meaning MM is greater than 1 to drive the AES core and simultaneously charge multiple others?
My gut reaction would be that connecting multiple capacitors to AES and charging multiple would increase randomization and therefore security.
More variables, more chaos, right?
That's the common assumption, and it's a perfectly logical one, but the paper's theory and experiments reveal the opposite.
Really?
Yeah. When capacitors are chosen to drive AES at the leakage point, all of them acquire a leakage component. Then if MIM capacitors are also chosen to connect to the supply at the immediate next time step, the probability of any of those M leakage carrying capacitors being connected to the supply increases significantly. Whoa! So instead of diluting the signal, it actually concentrates it more by increasing the chances that some capacitor carrying leakage will connect to the supply.
Precisely. The research provides a mathematical proof and strong experimental validation for this. It demonstrates that for M1, the probability of information leakage is significantly higher.
Give me an example.
Okay. For instance, with 10 capacitors total, N2010, and selecting 2 at a time, M2, the calculated probability of leakage jumps to 0.7, much higher chance of leakage compared to 0.2 when M1. Statistically, the attacker has a much higher likelihood of observing a leakage-carrying capacitor connect to the supply in the immediate next step.
That's truly mind-bending. So if I'm understanding this correctly, the big takeaway for designers isn't always more complexity equals more security. Here, simplifying the active selection to just one capacitor actually maximizes your protection. That's a truly counterintuitive revelation.
Absolutely. Both theoretical analysis and simulation experiments strongly confirm this. Choosing a single capacitor, M1, to drive the AES and a single capacitor to be charged from the supply at any given time is the optimal TVTF strategy for maximum physical time domain obfuscation.
Wow.
This configuration reduces information leakage by the highest possible amount. It's a testament to how deep the understanding of these physical phenomena needs to be to build truly secure systems.
That's a powerful and surprising conclusion. Sometimes simplifying the randomized selection process is actually more secure. Let's move on to the results. How did the TVTF concept perform in simulations and experiments, proving its efficacy?
Okay, so to evaluate the TVTF, the researchers first collected power traces from that 8-bit Atmel microcontroller running AES 128 encryption using the chip whisperer. This established a baseline.
The starting point.
Right. An unprotected AES 128 implementation showed an MTD of approximately 20 traces, meaning it could be broken very quickly, basically instantly.
So the starting point was a highly vulnerable system, which is a good testbed for a countermeasure. How did they go about optimizing the physical parameters for the TVTF, things like capacitor size and the resistance of the switches?
Good question. To minimize the area overhead, which is crucial for embedded devices where every millimeter of chip space counts, a total capacitance of 200 picofarads was chosen for the TVTF circuit.
Okay, 200 PF total.
Then they had to determine the optimal value for individual unit capacitors and the switch-on resistance to ensure no performance degradation of the crypto engine. Through careful analysis, they found that by tolerating a maximum voltage drop of sweet 1 volts across the AES core.
A small drop.
Yeah, very small. A minimum unit capacitance of 20 picofarads could be supported with a switch-on resistance of 10 ohms. This specific choice also set the maximum number of phases or individual capacitors at 10.
So they balanced area efficiency, performance, and the number of phases right from the start. What impact did increasing the number of phases N have on the security levels?
As expected, increasing the number of unit capacitors significantly improved the MTD. More phases introduce more randomization within a given time window, making it much harder for an attacker to find consistent leakage patterns.
More places for the leakage to hide.
Exactly. If you could visualize this, it would be like seeing the peak protection rise with each added phase.
But I'm guessing there's a limit or a trade-off there too. You can't just add infinite phases, right?
Exactly. While more phases boost MTD, they also increase power consumption due to higher switching frequencies and could potentially lead to larger voltage drops, impacting the AES engine's performance. So there's an optimal balance.
Finding the sweet spot.
Right. Based on their analysis, an optimal N of 10 was chosen for their design, balancing security gains with practical constraints.
And did the simulations confirm the crucial M1 rule you just explained? That picking a single capacitor at a time is the most secure?
Absolutely. The simulations strongly validated the theoretical finding. MTD decreases as the number of simultaneously chosen capacitors increases.
So more is definitely worse here.
Definitely. For a system with 10 total capacitors, N10, choosing M1 consistently yielded the maximum MTD. This further cemented that a single capacitor selection strategy, both for driving AES and for charging, is indeed the best for randomization and obfuscation.
Theory holds up in practice.
Yes. It's a powerful illustration.
And what was the impressive result of this optimized TVTF with N10 and M01? How much better was it?
With 10 equally distributed capacitors and M&N, the TVTF achieved an MTD of approximately 30,000 traces.
30,000 compared to 20.
Compared to 20, yeah. This represents a remarkable 1,500x improvement over the unprotected implementation. That's a significant leap in security, turning an instantaneous break into a much more arduous and time-consuming attack.
That's an impressive improvement just from smart design choices. Can they make it even more random or add another layer of obfuscation?
Yeah.
How does the periodicity of the pseudo-random number generator, or PRNG, come into play?
Good point. The randomness of the TVTF relies heavily on the quality and periodicity of the PRNG. The longer the periodicity of the PRNG.
How long before the random sequence repeats?
Exactly. The longer it is, the more unique the shuffling patterns become. This leads to a significant increase in MTD. A longer, less predictable sequence makes it much harder for an attacker to predict or reverse engineer the shuffling, as they can't simply wait for the pattern to repeat.
Okay, so the pseudo-randomness needs to be as pseudo-random as possible, like a deck of cards that's shuffled perfectly every time. What about the capacitors themselves? Could making them unequal add another layer of disguise?
Yes, this is another clever tuning knob they explored. Further randomization can be achieved by using slightly different capacitance values for the individual unit capacitors, even while keeping the total capacitance fixed.
So not all 10 capacitors are exactly 20 PF.
Right. For example, instead of all 20 PF capacitors for a 200 PF total, they explored a range from maybe 16 PF to 24 PF.
Why would varying the capacitance values help? I would think consistency would be better.
The reason is quite subtle. The residual voltage on a capacitor, which carries the leakage information, depends on its individual capacitance value. So, by introducing unevenness, each capacitor will store and leak slightly different voltage residues. This introduces additional signal distortion and complexity for an attacker trying to build a consistent leakage model, as the signature of the leakage is constantly changing in a subtle way.
And what was the impact of this unequal capacitor strategy? Did that extra layer of disguise make a significant difference?
It did. This technique provided an additional approximately 3x improvement, pushing the MTD to an impressive 96,000 traces.
Wow, nearly 100,000.
Yeah, which represents a staggering 5,000x improvement over the unprotected baseline. It truly showed the power of multi-layered obfuscation.
That's incredible. Any downside to making them too uneven?
Well, there is a consideration. Too much spread in capacitance values could increase the maximum voltage droop across the AES core, potentially impacting the circuit's efficiency or stability. So again, it's about finding that sweet spot for optimal distortion without compromising the chip's core function.
All right, always trade-offs. So beyond just MTD, how do they comprehensively analyze the security of TVTF against more advanced attacks? Attackers are always getting smarter, after all.
They employed several rigorous methods to stress test TVTF. First, they used Test Vector Leakage Assessment, or TVLA.
TVLA, what does that measure?
TVLA is crucial because it measures the amount of meaningful leakage present, not just how many traces it takes to break. The unprotected AES showed an extremely high T-value, around 190.1, indicating severe leakage.
Very leaky.
Very leaky. The TVTF-protected AES, however, maintained a much lower T-value with a maximum of 8.37 and only crossed the security threshold of 4.5 after 2,500 traces. This indicates good relative security, confirming that the TVTF is effectively reducing exploitable information to a much safer level.
That's a good sanity check beyond just MTD, showing the quality of the protection.
Yeah.
What about more sophisticated CPA attacks? An attacker might try to integrate traces over a larger window to capture scattered leakage.
Absolutely. Attackers might try a sliding window-based integrated trace attack. This is where they integrate power traces over a larger time window to try and capture multiple obfuscated leakage points that might be scattered by the TVTF's randomization.
Does TVTF resist that?
It does. Even against this advanced technique, TVTF showed a robust MTD of 15,000 traces, demonstrating remarkable resilience. This is largely due to the fact that integrating obfuscated signals also effectively amplifies the noise.
Oh, interesting.
Yeah, so the signal-to-noise ratio gets even lower for the attacker, which is kind of self-defeating for them.
And what about simply averaging traces? That's a common technique attackers use to reduce measurement noise and get a cleaner signal for analysis. Did TVTF hold up against that?
They tested against that too. Attackers often average multiple traces for the same plaintext or key to suppress measurement noise and obtain a cleaner power trace. The TVTF was tested against 200x average traces and still showed a robust MTD of 96,000.
Still 96,000 even after averaging.
Yeah. Yep. This confirms its effectiveness even when an attacker attempts to suppress the inherent noise and obfuscation in measurements, demonstrating a very high level of protection.
So it's holding up against some of the best attack methods, which is incredibly encouraging. Now let's talk practicalities. What about the overheads? Are we talking about massive power and area penalties for all this security? Because that's usually the catch.
This is where TVTF really shines and differentiates itself from many other countermeasures we discussed earlier. The power overhead.
The extra power needed.
Right. Including charging the capacitors, the rapid switching, and running the PRNG, it was calculated to be approximately 325 microwatts. Relative to the power consumption of the AES core itself, this is only about 1.24x, or a 24% increase.
A 24% increase in power for that level of protection seems quite reasonable, especially for many IoT devices that already have fairly tight power budgets.
It's very competitive, yes.
And what about the physical size, the area on the chip?
Mm-hmm.
That's another critical factor for miniaturized devices.
The area overhead, which counts for the capacitors, the PRNG logic, and the switches, was approximately 0.03 square millimeters. Relative to the AES core's area, this amounts to only about 1.2x, or a 20% increase.
Only 20% bigger.
Yep. And crucially, all this comes with no performance degradation of the cryptographic engine itself.
No slowdown.
No slowdown. If you compare this against the 3x area and 4x power overheads of some other techniques we talked about, TVTF's overheads are incredibly favorable.
That's fantastic. Low overheads are a huge factor for commercial viability and widespread adoption. And how generic and adaptable is this solution? Can it be used for anything beyond this specific AES 128 example?
The TVTF countermeasure is truly generic, which is one of its most powerful strengths. It can be used as a wrapper for both hardware and software implementations of AES, or indeed any other encryption engine.
Any crypto core.
Pretty much. The research demonstrated that if the initial MTD of an unprotected system is already higher, for example, around 210 for a hardware AES on an FPGA TVTF can push that MTD to over 1 million.
Over 1 million traces.
Yeah, offering even greater protection in those scenarios, this adaptability makes it incredibly powerful and widely applicable across diverse embedded systems.
This sounds incredibly promising in simulation, but the real test, of course, is in the physical world. What happened when they brought this concept to actual silicon, fabricating a real microchip?
This is the ultimate validation, right? Moving from theory and simulation to tangible hardware. To truly prove the concept, the researchers fabricated a 65mm TSMC CMOS integrated circuit, or IC, incorporating the TVTF design.
A real chip.
A real chip. They chose AES 256 as the test encryption engine for this real-world implementation. The image of this prototype chip, its die micrograph, is quite striking.
So they built a chip with and without the TVTF to compare directly. What did the power traces look like on this physical hardware? Could they visually see the obfuscation at work?
Absolutely, and the results were stark. Power traces from the unprotected AES clearly showed distinct, repeatable operational cycles. You could literally see the encryption rounds taking place in the power consumption waveform.
Clear pattern.
It's very clear. In dramatic contrast, the TVTF-protected AES traces for the exact same region showed no clearly visible operational cycles. The signal was effectively obfuscated into a noisy, indistinguishable mess.
Wow.
This was direct visual proof of the time domain obfuscation at work on real silicon.
That's amazing visual confirmation that it's actually scrambling the signal, making it unreadable to the human eye. But how did it perform against a CPA attack in this real-world IC? Did it live up to the promise?
Okay, so using a Hamming distance, or HD, attack model, which is suitable for hardware implementation.
Right, the bit flip model.
Exactly. The unprotected AES 256 revealed its correct key byte within 6,600 traces.
Okay, 6,600. Still pretty fast.
Relatively low, yeah. Confirming its vulnerability in a real-world scenario. However, the TVTF AES 256 in the same test did not reveal the correct key until an astounding 3.4 million traces.
3.4 million traces. That is a monumental difference in the real world.
Huge difference.
That moves it from a matter of minutes or hours to something practically impossible for an attacker.
Indeed, this represents a 500x improvement in MTD in a real-world silicon implementation. It's a massive leap forward in practical security for embedded cryptographic devices.
That's a huge win for practical security. But I noticed a number there, 500x improvement in the IC versus the 5,000x improvement seen in simulation. Why the gap? What happened to the other factor of 10?
That's a crucial observation, and the researchers thoroughly investigated it. While 500x is still a significant achievement, the difference in performance highlights an important aspect of real-world implementation versus idealized simulation.
The real world isn't perfect.
Exactly. The IC implementation used transmission gates, or TGs, for the switches in the switched capacitor network. To ensure these switches could provide adequate current and maintain a very small time constant, which is necessary to avoid performance degradation of the AES core, the WL ratio, essentially the physical size, of these transmission gates had to be increased.
So they needed bigger switches for better current flow and speed. But what was the unintended consequence of that?
Unfortunately, increasing the size of the transmission gates led to higher static leakage current through the switches.
Static leakage. Current leaking even when it's off.
Kind of, yeah. Think of these switches like tiny gates. In simulation, we often assume they're perfect, completely shut off when they should be. But in the real chip, to make them fast enough not to slow down the encryption, they had to make them slightly leaky. So even when they were supposed to be off, a tiny, almost imperceptible trickle of data-dependent electricity was still getting through. This subtle static leakage inadvertently provided a small but consistent side channel, allowing the correct key to be retrieved quicker than the simulations, which often assume ideal switch behavior, had predicted.
So a practical design choice to maintain performance unintentionally created a new, albeit smaller, leakage path. That's a classic engineering trade-off.
It really is.
What's the implication for future development then?
This finding highlights a clear path forward for further improvement. The immediate next step is to explore and integrate different types of low-leakage switches into the design. By minimizing this static leakage, they anticipate closing that gap between simulated and measured performance, pushing the real-world MTD even higher.
Getting closer to that 5000x.
That would be the goal, yeah. Achieving even greater resilience.
That's a great example of how research evolves in the face of real-world challenges. Now, looking ahead, this research provides some very specific tuning knobs for security engineers. What are these key factors that can further enhance TVTF's resistance?
Yeah, this research provides very clear guidance on how engineers can further increase the immunity of TVTF, allowing them to balance security needs with other design constraints. The first major tuning knob is the number of phases.
More capacitors.
Right. As we saw, increasing the number of unit capacitors or phases directly increases the randomization within a given time window, thus boosting the MTD. More phases mean the leakage is spread across more potential paths, making it harder to track.
So generally, more phases means more security, assuming the power and area overheads are manageable. What's the next tuning knob?
The second is the use of uneven capacitors. By making the individual unit capacitor values slightly different, while crucially keeping the total capacitance fixed, an additional layer of signal distortion is introduced.
That's slight variation.
Exactly. The residue voltage on a capacitor depends on its individual capacitance value, so this unevenness further reduces information leakage, making the attacker's job even harder.
So, introducing subtle physical variations adds another layer of disguise to the signal. And finally, the randomness source itself.
Exactly. The third tuning knob is the periodicity of the PRNG, the pseudo-random number generator. Utilizing PRNGs with higher periodicity ensures more random shuffling patterns. This directly contributes to greater MTD.
A longer random sequence is better.
Much better. A longer, less predictable sequence means the attacker cannot easily map or reverse engineer the switching pattern, giving them no repeating cycle to exploit.
So these are practical ways for engineers to scale the security based on the specific needs of a device. To sum up, what are TBTF's core strengths that make it such a significant countermeasure against side-channel attacks?
Okay, TBTF offers a compelling combination of advantages. Firstly, it's truly generic. It can protect any encryption engine, unlike many algorithm-specific shuffling techniques.
Works with anything.
Pretty much. Secondly, it boasts low overhead, only approximately 1.2x area and 1.25x power overhead, which is critical for resource-constrained IoT devices.
Cheap and small.
Relatively, yes. Thirdly, it's digital-friendly and synthesizable. The capacitors can be implemented using standard digital library cells, and the rest is fully digital logic, ensuring scalability across different fabrication technologies without complex analog design.
Easy to build and scale.
Right. And the level of protection it offers, both in simulation and real-world silicon.
The security itself.
It provides high protection, approximately 5,000x protection in simulation, and a proven 500x improvement in real-world silicon, all without any performance degradation of the crypto engine.
Great protection, no slowdown.
And lastly, it's readily integrable. Commercial microcontrollers often have built-in true random number generators, which can be easily leveraged as strong seed generators for TVTF's randomization, further boosting its security without additional hardware.
Uses existing features. Very practical.
Very practical.
Those are incredibly strong points, making it a very practical solution. What are the immediate and long-term future directions for this technology?
The immediate next step is crucial: to explore and integrate low-leakage switches into the design. This is vital for bridging that gap between the phenomenal simulated performance and the impressive but slightly lower measured performance in the fabricated IC.
Closing the gap.
Exactly. Reducing that static leakage is key to maximizing its real-world effectiveness.
And beyond just power side-channel attacks, could this concept of physical randomization extend to other types of side channels as well, like EM?
Potentially, yes. There's significant future potential to extend this solution to protect against EM side-channel attacks as well.
Electromagnetic leakage.
Right. This could be achieved by strategically implementing the capacitor shuffling logic and the AES charging logic in low-level metal layers of the IC. These lower layers are inherently known to radiate less electromagnetic leakage, offering another layer of physical obfuscation.
So hiding it deeper in the chip.
Essentially, yeah, defeating even more forms of eavesdropping.
Okay, let's bring it all back home. This has been a truly fascinating deep dive into a cutting-edge area of cybersecurity.
Absolutely. The aha moment for me is truly understanding that mathematically secure doesn't always translate to physically secure. The subtle, almost imperceptible power fluctuations from your embedded devices, from your smart doorbell to your car's engine control unit, can be a surprisingly effective side channel for attackers to extract secret keys.
But the beauty of this research is that with clever engineering, by introducing something like a physical time-varying transfer function, we can scramble that leakage in the time domain. We can effectively make the invisible power whispers illegible to an attacker.
It's like turning a clear radio signal into static, making it impossible to decipher.
Exactly. And why this matters to you, the listener, is clear. This isn't just academic research confined to a lab. It's a practical, low-overhead solution that could be integrated into the next generation of IoT devices, microcontrollers, and smart systems,
making them dramatically more resilient against one of the most insidious forms of attack, protecting your data not just in the abstract cloud, but right down to the silicon itself.
It makes you think, doesn't it? As our digital lives become more and more embedded in physical devices all around us in our homes, our cars, our wearables, what other invisible leakages might we need to protect against? And how might we apply similar principles of physical randomization and obfuscation to keep our data truly safe in an increasingly connected and inherently vulnerable world?
A profound thought to leave you with, indeed. Where else can we physically scramble the signals?
Thank you for joining us on this deep dive into the physical security of our digital lives. We'll catch you next time.